Our bodies are full of incredible paradoxes. And we're about to dive into one of the biggest, a process called intimal hyperplasia. It's a true double-edged sword. On one hand, it's a fundamental healing response that's absolutely essential for our survival. But on the other, it's a primary reason why so many life-saving medical procedures can ultimately fail. I mean, just look at this. On one side, you have this incredible adaptive force that's critical for our survival and growth, right from the moment we're born. And on the other side, you have this pathologic or harmful response that's a leading cause of failure for things like bypasses and angioplasties. So how can one single process be both the hero and the villain? Well, let's get into it. So let's start with this biological paradox itself. What exactly is this double-edged healing process we're talking about? Okay, so at its core, intimal hyperplasia is really just the thickening of a blood vessel's inner wall. That's the intimal layer. You can think of it as the body's natural way of patching things up or adapting when things change. It's a really fundamental healing response that's just hardwired into our biology. And this brings us to the million-dollar question, the one that drives so much medical research. How does a response that's so vital for life turn against us? What's the switch that flips this healing process from helpful to harmful? To really understand how it all goes wrong, we first got to appreciate all the times it goes right. So let's look at the hero side of the story, the body's amazing and absolutely necessary remodeling process. This process is critical from the second we're born. I mean, it literally helps reroute our entire circulatory system from fetal circulation to breathing air. It's incredible. As we grow up, it helps our arteries adapt and strengthen. And get this, in a bypass surgery, when a surgeon uses a vein to replace an artery, this same process helps that vein arterialize, basically making it thicken up so it can handle much higher blood pressure. It's truly amazing stuff. Okay, so that's the hero, a powerful, adaptive force for good. But what happens when that process gets a little overzealous? This is where the villain emerges. Probably the best way to picture this is with an analogy. Imagine a road crew gets sent to fix one little pothole. They do a great job, but then they just keep paving. They pave over the whole lane, then the other lane, and pretty soon the entire road is blocked and nothing can get through. That's basically what's happening inside our blood vessels. It's an over-enthusiastic repair crew that just doesn't know when to stop. So, how does this road blockage actually happen in our bodies? It's a whole cascade of events, usually kicked off by an injury, like from a common procedure like angioplasty. First, that injury sounds the alarm, and platelets and inflammatory cells rush to the scene. Next, hearing those alarm bells, smooth muscle cells, kind of like the body's construction workers, they migrate from the middle layer of the vessel into that inner layer and start multiplying like crazy. They get to work building up this new material, creating what's called a neo-intima, a new, thickened inner layer. And the end result of all this frantic construction, the vessel gets narrower and narrower, a condition we call stenosis. And this whole process, it doesn't happen overnight. The initial alarm is fast. We're talking platelets showing up within hours. But the real problem builds up over time. Over the next few weeks, those smooth muscle cells move in and multiply. Then, for months, that matrix just keeps building up, thickening that vessel wall for the worse. But wait, it actually gets worse, because on top of that inner wall getting thicker and thicker, the entire vessel can start to shrink on itself. It's a process called negative remodeling. So it's like the walls are closing in from the inside and the outside, choking off that blood flow even more. So what decides how bad this gets? Well, it turns out there are a few key factors that can really add fuel to this fire, making that healing response way more aggressive than it should be. Yeah, a few big things really supercharge this process. First, the severity of the initial injury. That's a huge one. More damage equals a more aggressive healing response. But underlying health conditions also play a massive role. Things like diabetes and high cholesterol are known to just pour gasoline on this fire. In fact, the source material we reviewed puts it bluntly, saying diabetes is a predictor for augmented intimal hyperplasia and restenosis. What that means in plain English is that diabetes creates an environment in the body where this overhealing is just far more likely to happen and to be much, much more severe when it does. In our lifestyle choices, they are absolutely critical. Get this. In experimental models, cigarette smoke doubled the amount of intimal hyperplasia, a twofold increase. That is a powerful, direct link between a personal choice and this really dangerous biological response. So all of this brings us to a huge modern medical dilemma. Knowing what we know, how in the world do we fight against this failure? How do we control this over-exuberant healing? Let's look at one of the main battlegrounds, stents. First, we had bare metal stents. Now, these are great at physically propping the vessel open and stopping that negative remodeling we talked about. But because it's a foreign object, the body mounts a really strong healing response against it, which is the very thing we're trying to stop. So to solve that, we developed drug-eluting stents. These release drugs to suppress that healing. The problem? Sometimes they suppress it too much, and they delay the necessary, good healing of the vessel's inner lining. And that right there, that is the core challenge for modern medicine. Whether we're talking about drug-eluting stents or drug-coated balloons, the very treatments that are designed to stop the overhealing also slow down the necessary healing. It's this incredibly delicate balancing act, and if you get it wrong, you can create totally new risks, like a clot forming in the stent months or even years later. So this leaves us with this one fundamental question, the ultimate challenge for researchers today. How do we send a message to the body that says, hey, heal this injury, but also says, and know when to stop? How do we harness the hero without unleashing the villain?